Hello friends, welcome to my channel, and this is part 5 of electricity and magnetism paper solution of Guwahati University 2022 physics honors, and this is part 5. uh, Part 1 to part 4 are given in the link of this video, so from part 1 to part 4 are given in the description box. So now before we start, please subscribe the channel if you are new to my channel. Also share with your friends if you think my videos are helpful, and also hit the thumbs up button if you like my videos. So now let's start. So here is question number 4a. So using Gauss law, find the expression for electric field due to a spherical charge distribution of charge densities rho at outside point and on the surface at a point inside the sphere. That means at an inside point. So now let's start. So here we have considered this is a sphere, right, of radius capital R. Radius of this sphere is capital R, and we have taken a point outside the sphere. This is the point P. This is the point P outside the sphere. I hope you can see this. So now we need to find the electric field at this point, right? And here we have drawn a Gaussian surface. Here you can see the dotted lines. So this is Gaussian surface through this point, right? And we have taken a surface element, very small surface element ds, and we know the area vector. If this is the face of this area element, then that area vector is perpendicular to this area element, and so here is the direction of this area element vector, ds vector. Okay, so this is the E vector, that is electric field, right? So, and the distance of the point P from the center of this sphere is small r. We have taken small r, and this O is the center of the sphere. Okay, so here you see the charge density rho, that's going to be given by, so we have considered the total amount of charge enclosed by this distributed in this cylinder, in this sphere, is suppose Q. So Q is uniformly distributed, right? So then total charge Q by its volume, Q by volume, that's gonna be the charge density, right? So volume of a sphere is 4/3 pi r cube. Here capital R is the radius of this sphere, right? So that's why Q by 4 pi r cube. So hope you have understood this. This is the value of rho. So at a point outside the solid sphere, that means we are talking about the point which is lying outside the sphere. So this is the sphere and this is the point outside the sphere, right? So now you see, so we have drawn a Gaussian surface. This dotted line represents Gaussian surface of radius r, right? So now you see electric field is directed radially outward. So this is the direction of E, that is radially outward, due to positive charge. We have taken a positive charge here. We have considered that the charge distributed is positive, right? We have considered here on which positive charge Q is uniformly distributed, right? So charge distributed on this sphere is positively charged, right? So this should be radially outward. Now according to Gauss theorem, electric field, electric flux, so that is given by E vector dot S vector into surface integral of this, and according to Gauss theorem, that's equal to 1 by E naught times 1 by epsilon naught times, not E naught, epsilon naught times of Q, right? That is what we have got here. Okay, and dot product of two vector, vector E and vector ds, I think that there is a printing mistake. That should not be E S. I think it should be E ds cos theta. Integration surface integral E ds cos theta is equal to q by epsilon naught, right? So that should be the correct. So here we have a printing mistake. Okay, so hope you have got it. So now you see, if you see the diagram here, the direction of these two, vector E, that is radially outward, and the direction of the area vector, which is normal to this surface element, right? They are along the same direction. That's why angle between these two vectors is 0. Theta is equal to 0. That is why if you put here 0, cos 0 degree is 1, right? This is theta. So cos 0 is 1. That's why we're gonna get surface integral of EDS is q by epsilon naught, right? So now you see, E is same at all the points on the Gaussian surface. So the value, this you see, electric field intensity E, right? Its magnitude is constant at all the points on this Gaussian surface. So that is why we can consider this one as constant. So we can keep this E outside the integral. So that is why we have got E surface integral of ds q by epsilon naught. This is q by epsilon naught, right? So this is what we have taken. This is equation number 1. Now surface integral of ds is equal to the surface area of the spherical Gaussian surface, and that is equal to 4 pi r square. So we have taken the radius of this Gaussian surface is small r, and total surface area of a sphere is 4 pi r square. So that's why here you see, that's why integration surface integral ds, that's gonna be equal to 4 pi r square. Sorry, let me write it properly. Surface integral of ds, that's gonna be equal to 4 pi r square. So if you put this result here in equation number 1, then this equation number 1 implies this is replaced by this value, right? E into 4 pi r square q by epsilon naught, and that implies here you see E is equal to 1 by 4 pi epsilon naught q by r square, right? And this is the electric field outside at a point outside the sphere, right? This is the electric field, and you can see this is this result is same as the result as the electric field at a point due to a positive charge q, right? So we can consider the amount of charge distributed over this uniform over this surface, spherical surface is concentrated at the center. You can consider that way, right? So hope you have understood this topic. Now let's go to the point on the surface. So here you see we have got the expression, this E is equal to, we have got the result for outside the surface. E is equal to 1 by 4 pi epsilon naught q by r square. So on the surface, so the small r will be equal to capital R, because this Gaussian surface will coincide the sphere, right? So capital R is gonna be equal if this p point lies on this surface, on this sphere, right? So that's why small r will be equal to capital R. In that case, E will be equal to 1 by 4 pi epsilon naught q by capital R square, right? Capital R square. Now you see from here we can evaluate q from this relation. Q will be equal to 4 by 3 pi r cube into rho, right, into rho. So you can replace this q by this result as well. So if you use this value of q here, then what you will get, this expression, this suppose this one, let me clean this part. So what we have got, electric field at a point outside the sphere is, we have got 1 by 4 pi epsilon naught q by r square. So let us replace the q by this value. Then what you will get, 1 by 4 pi epsilon naught 4 by 3 pi capital R cube rho by small r square. So here you can see clearly this pi cancels, and this 4 cancels. So what we're going to get, 1 by 3 epsilon naught r cube rho by r square, right? That's what we're gonna get. So this is the, let me clean this. So this is the electric field at a point outside the sphere, at the point P outside the sphere, right? So hope you have understood this. Now at a point on the surface of the sphere that is given by this, so here small r is replaced by capital R. Again, if you put the value of q, then what you're going to get here, you see. So after putting the value of q, this value of q, here we have got the expression E is equal to 1 by 3 epsilon naught capital R cube by small r square rho. So if small r becomes equal to capital R, then what you will get, so what we have got, E is equal to 1 by 3 epsilon naught capital R cube rho by small r. So on the surface, so small r is equal to capital R. In that case, E is equal to 1 by 3 epsilon naught capital R cube by rho. So small r is replaced by capital R square. Here is square. So this is gonna cancel this. So our result will be 1 by 3 epsilon naught r rho. That is what we will get. Now you see. Now let us take the third case at a point inside the solid sphere. So here you see, now this point, we are taking this point at so this is the sphere, you can see, right? And we are taking the point here inside the sphere. This is the point P. So hope you can see this, right? And this is a very small area element ds, right? And this is the vector ds, vector area vector, and along the same direction we have vector E, right? And this is the point P, and here you see the radius of this sphere is capital R, and we have taken this dotted line represents a Gaussian surface through the point P of radius is small r. Its radius is small r. So P is the distance of P from the origin O is small r. So hope you have understood this. So now you see here the surge enclosed by the Gaussian surface. So now as we are taking the point inside the sphere, okay, so now we have to take the charge which is distributed within this part of the sphere, right? Not the surge in whole sphere, because now this P is inside this sphere, right? So that's why uh, we have to take the charge enclosed by this Gaussian surface which is drawn through the point P. So hope you have got this point what I am trying to say. So now you see, so here the charge enclosed by this Gaussian surface we have taken Q dash, suppose. So total charge was Q, and volume of the Gaussian surface, volume of the sphere is now, here you can see, you know, that charge density is rho. So if you multiply Q by rho with the volume charge density is rho, so which is given by Q by the total volume of the sphere, that is 4 by 3 pi r cube. Here pi, capital R cube, is the radius of the sphere. So what gonna be the charge enclosed by this Gaussian surface, right? Here you see, so volume of the Gaussian surface, that's gonna be 4 by 3 pi 4 by 3 pi small r cube, because small r is the radius of the Gaussian surface, then volume into charge density, that's going to give you the charge enclosed by this Gaussian surface. So hope you have understood this. So now you see, so as I have told you that charge density rho into volume of the Gaussian surface, this is Gaussian volume of the Gaussian surface, gonna give you the charge enclosed by the Gaussian surface. So here the rho is nothing but Q by Q, that is the total charge distributed on this in this sphere, and so that is Q, and that is why density will be given by Q by volume of this sphere, 4 by 3 pi r cube. So hope you have understood this. This is Q dash, right? This is Q dash. So now doing so, what we have got here, let me write these things. Here you can see Q dash, that is equal to Q by 4 by 3 pi capital R cube into the volume of the Gaussian surface 4 by 3 pi small r cube. Here this pi cancel, 4 cancel, 3 cancels. So what we have got? We have got Q dash is equal to Q small r cube divided by capital R cube. So that is the charge enclosed by this Gaussian surface for the which is passing through the point P, which is inside the sphere. So according to the Gauss theorem again, that electric flux, which is surface integral of vector E dot vector ds, that's gonna be now 1 by epsilon times of Q dash. Q dash is the charge enclosed by the Gaussian surface now. So that's why we're gonna take Q dash instead of Q, right? So that's why here we have got Q dash by epsilon naught, right? So let's use this value of Q dash here. So that is what Q capital small r by Q small r cube by capital R cube. And doing so, what we have got, let me clean this. So let me use this value of Q dash here. So what we will get here, integration E dot ds, that's going to be equal to Q small r cube by capital R cube divided by epsilon naught, and that's going to be equal to Q small r cube by capital R cube epsilon naught. That's what we will get, right? Now again we're going to use the dot product concept of dot product, that is surface integration E dot ds cos theta. So here theta will be again 0, right? Theta will be again 0 degree, and cos 0 is 1, that's why E dot ds. So here where we have got, so here you can see E ds cos 0 is 1, and E is constant at each and every point on the Gaussian surface. So that's why this E is taken out, and surface integral of ds, that's going to be equal to this, right? That is what we have got here. So hope you have understood this. Now let me clean this. Now you can see the surface area of this Gaussian surface, that is 4 pi small r square, 4 pi small r square, right? So here we can replace the small surface integral over ds by this 4 pi r square, and doing so this expression becomes E into 4 pi r square, which is written here, is equal to q r cube by capital R cube, epsilon not here, epsilon capital R cube. So here R cube R square cancels R cube here. So, and also is there something else that gonna be cancelled? No, nothing. Now you see, if you use this value of ds, surface integral over ds, that means this one is equal to 4 pi r square. If you use here in this expression, so then this will implies this. That means, let me write here what we will get. We're gonna get E, instead of integration ds, we're gonna write 4 pi r square, right? That is nothing but area of the Gaussian surface is equal to q small r cube by capital epsilon not capital R cube, right? Epsilon not capital R cube. So this implies E is equal to q r by 4 pi epsilon naught capital R cube. That is what we get. This is the electric field for a point inside the surface, inside the sphere. So let me clear one more thing. This is the expression for electric field. This is point on the surface of the sphere. It comes from this equation after replacing q by this value, that is 4 by 3 pi r cube into rho, right? So now you see, now if you put the value of q here, then what gonna be the expression? This equation. That is what I have written here. Okay, so if you replace this q by q is equal to 4 by 3 pi capital R cube into rho, right, then what you will get? So here you can see this 4 will be cancelled, right? So what will be the result? Let me write here. Just let me take one more slide. So here what we have got, E is equal to QR by, let me write the final expression again. So final expression that we have got electric field for a point inside the sphere, E is equal to 1 by 4 pi epsilon naught R cube, and here we have QR. Now let us replace the QR by 4 by 3 pi capital R cube by into rho. Here 4 pi epsilon naught R cube. So here R cube gone, pi gone, then 4 also gone. So what we have got, 1 by 3 epsilon naught, and here we have rho. So this is the result we're gonna get. So if you use the value of Q is equal to 4 by 3 pi r, this is capital R cube, into rho. Rho is the volume density, charge density, and this is the volume of the sphere, right? Volume into charge density, that's gonna give you the charge, right? And charge per volume gonna give you the charge density, right? So hope you understood this things, very simple, right? So this is the expression for electric field for a point inside the sphere. So we have got, I have missed this small r here, right? 1 by 3, sorry, let me write rho r by 3 epsilon naught. So this is the electric field at a point which is inside the sphere. This is the sphere, and this is the point P, which is at a distance of a small r from the center, and the Gaussian surface is drawn through this point. So hope you have understood. This is the expression for a point inside the sphere, right? Now let's move on to next question. Now, using Gauss law, find electric field due to a infinite plane sheet of charge having charge density sigma. Suppose we have an infinite plane sheet, and this is positively charged plate, suppose. Let me consider that way, right? So we need to find electric field due to this plane sheet, right? And the charge density is sigma here. Sigma is the charge density, right? So for that purpose, we need to draw a Gaussian surface here, right? So this is the Gaussian surface. Let me consider. Sorry. So let me take this one. So this is the Gaussian surface, which is cylindrical in shape, right? And the area of cross section we have considered, that is A. Area of cross section is suppose A. Let me write here. Area of cross section is A. Okay. So this Gaussian surface is drawn through the point P, which is at a distance of r from this surface, and this is the point P, right? This is the point P, and we need to find the electric field at this point P. Okay, so now you see, you can see this diagram. So this is the very small element, area element ds. Its area vector is pointed in this towards in this direction, and this is the electric field, direction of electric field. And here this n cap represents unit vector along the area vector, right? So, and the distance of this point P is r from the sheet, right? And so here is the point. Let me take another point P dash, which is also at the same distance, at a distance r from the sheet, right? So this is the direction of electric field in this way, and this is the area vector ds, right? This is, we have taken 2, this is 1, and the surface which is on the plane sheet is suppose 3, and the charge density is sigma. Okay, and this plate is suppose positively charged. We have assumed that way, right? So according to Gauss theorem, we should get this, and this Q here, you see, if sigma is the surface charge density, surface charge density, and the surface area S. So here you see, this S is the area of this inch of this Gaussian surface. So hope you have understood this, what is S here. So if sigma is the surface charge density, then surface area S into sigma gives you the charge, right? Because surface charge density is given by charge by surface area, right? So hope you have understood this. This is equation number 1. Now Gaussian surface is divided into 3 parts, 1, 2 and 3. N keeps the curved surface and of the cylinder as shown in the figure. This figure, don't write here 10, as shown in the right here adjacent figure. Okay, so now you see this equation 1 becomes, so this equation 1 can be written as sum of these 3, right? Sum of these 3 integrals. Okay, so you see this third is the curved surface. This third surface you can see here, number 3, it represents the curved surface. Okay, not this surface, not this one, this cross section. It doesn't mean the cross section. Okay, this number 3 represents the curved surface of this cylinder. Okay, remember this. So now you see angle between E and DS 90 degree for the curved surface, for this curved surface of this Gaussian surface. This is the Gaussian surface. In this case, this is the suppose area element ds, then this should be its direction should be like this way, that normal to the surface, and the electric field is radially, so electric field is in this direction as shown in the figure, right? So that's why the angle between these two is 90 degree, right? So you can see cos 90 degree, so here theta will be 90, cos 90 is 0, so this becomes 0, right? Electric flux through the Gaussian surface, curved surface of the Gaussian surface is 0. That's what we have got. Then equation number 2, this is suppose equation number 2. So this term here you can see, as it becomes 0 due to the, here I have already explained, due to the angle between the two vectors, area vector and E, that is 90, and cos 90 is 0. That's why this third part become 0, right? So that's why this equation number 2 is reduced to this form, right? This form. Now, since angle between E and DS for the surface 1 and 2 is 0, so for these two surfaces, two end surfaces, so here you see this is the DS and its area vector is in this direction, E also is in this direction, same direction, right? So here theta will be 0, so cos 0 is 1, so that's why this equation gives this result, right? E dot ds is eds cos 0, here theta is 0, so that's why this cos 0 will be 1, so we're gonna get eds only, right? Similarly here also, so this becomes, now as you can see the electric field intensity E is constant every point. Let me go to the next slide. So electric field intensity E is constant at every point in the Gaussian surface, so we can write E outside the integral, and integration of this ds, that's this one, here you see, if you integrate this surface element ds, this small surface element ds, here this is the face 1, suppose this is the face 1, then if you integrate this, then you're gonna get the whole face. The area of this whole face is, we have taken here S. Okay, so just let me go to the first page. Here you can see I have written here A, right? So it should be S, so I have taken here capital S. Surface area of this area of cross section is S. So here you can see, so ES, here also we have ES, right? Because both ends are of equal area, S, right? So that's why 2ES gives this result, so E will be equal to sigma by 2 epsilon naught. So this is the electric field at a point due to a infinite plane sheet of charge density is sigma. So hope you have understood. And this result in the vector form can be written in this way, where n is the unit vector perpendicular to the plane sheet pointing away from it. The electric field is directed away from the sheet if it is positively charged. So as we have imagined or assumed that this infinite charge sheet is positively charged, so that's why the electric field must be going away from this positive charge. Okay, always remember direction of electric field is always away from positive charge. Okay, so and perpendicular to this sheet, so that's why we have taken the field E direction in this way and in that way, not towards this direction. So hope you have understood this. So this is the next question. What is the electrical image? Find out the potential electric field and induce charge in density on the earth conductor plan. Okay, earth conductor plan. Okay, so now you see, so this is the definition of electrical image. The charge of opposite in nature, assume at a point symmetrically opposite to the charge on the other side of the conducting surface, treating the conducting surface as a mirror, is called optical image. So that means, you see, suppose we have a conducting surface, this is a conducting surface, and we have a charge on this side, this is Q. Okay, and this is not very far away from this surface. Okay, so due to this Q, there will be induced charge. Okay, so if this is positively charged, then induced charge will be negative in nature. So now you see, the electric field due to this charge should be normal to this surface like this. Okay, so now you see, we can, if you assume a similar same amount of charge here Q, but opposite in nature, this is minus, and at equal distance, suppose the distance from this surface to this positive Q is d, and if you assume the other side, that is minus Q, on the other side at the same distance d from the surface, so that potential at this on this surface is 0, then this Q is called electrical image of this positive Q. So hope you have understood this. So now let us move on to next part of this question, that is find out the potential electrical field and induce charge density on the earth conductor plan. Okay, so here you see, suppose we have considered this is the plan, conducting surface, you can see here, you can see on the xy plane. So we have considered on xy plane, this is the conducting surface. Okay, now here is the charge Q positive at a distance d, from this conducting surface, this is infinite conducting surface. From this surface, this positive Q is at a distance of d on the z-axis, right, on z-axis. So its coordinate is suppose 0, 0 d, right, and suppose here you see, and let us take, this is minus Q, we have assumed minus Q on the other side of this conducting surface. It's the coordinate is 0, 0 minus d, and this is image charge. Okay, this is the image charge. So at the same distance d from the conducting surface, right? So we are to find electric potential on the surface, that is obviously 0, and electric field on that surface, then charge density on the surface. So let us find first, let us take a point here, and this is the coordinate x, y, z. Okay, so before we find a potential, though we are to find potential on the surface, let us first find potential at this point first, at this point P first. Okay, so now you see here vector r is the position vector of P. now you can see that this P is at the coordinate x comma y comma z. So that's why if you see, then what will be this distance here? You can see, so from this xy plane, from this xy plane, this is at a distance of z, right? It is at as here you can see z distance from the xy plane, this conducting surface, and the distance from the, let us find the distance from the z axis to P. How to find that? First, let me draw a perpendicular on the conducting surface. So now let us find the distance from the origin to this perpendicular, the point where the perpendicular is drawn on the surface. So how to find that? This distance from the origin to the foot point of this perpendicular will be the distance from the z-axis to the point P, right? So hope you have understood this diagram. So now let's find this distance, okay, from the origin to the point on which at which the perpendicular from the point P is drawn. So here you can see, so now you see this point is y distance away from the x-axis, because the coordinate is x, y, z. We are taking coordinate is x, y, z, and this distance, this is x and this is y, and angle between them must be 90 degree. And if you use Pythagoras theorem, then this length should be root over x square plus y square plus z square. So now you see, so this is root over x square plus y square, right? Now you can see, if this distance is d, then what will be the distance, what will be the length of this part? What will be the length of this part? So here you see, from origin to this point, that length is z, right? So therefore length of this part must be z minus d. So this is z minus d, right? Z minus d, this length is z minus d. So therefore what will be the distance of this point P from the positive charge, right? So distance between positive charge and the point P, that will be equal to, if you apply the Pythagoras theorem, this is 90 degree, right? So this is perpendicular distance from z-axis to point P. So that's why this must be the hypotenuse, right? This must be hypotenuse. So now if you use the Pythagoras theorem, then what you're gonna get? Root over perpendicular square, that is root over x square plus y square whole square plus z minus d whole square. That's what you are gonna get, right? So that will be equal to x square plus y square plus z minus d whole square, right? So again you see, what will be the distance from this negative q charge to point P? So let us find it. So let me take another color here, you can see. So from this negative charge to point P, so what will be this distance? Now you can see here, this distance is d, right? This distance is d, and this length is z. So here you can see, if you take this point, they take these 3 points, so this one and this one and these 3 points. So because this plane is 2D, that's why it is difficult to show the perfect diagram. So here you can see, hope you can imagine this. So this is the point Z, suppose this is the point P, then this should be something like this, right? This is the minus Q and this is Z. So here you see, this length is so here you see, the origins must be lying between this point and minus Q. So this distance is d, and from the origin to this point, this length is z. This length is z, right? So therefore this side will be z plus d, and this is already known, that is root over x square plus y square, right? Now again, if you apply the Pythagoras theorem, the length or the distance from the minus q surge to point P, that will be root over x square plus y square whole square plus z plus d whole square, and that's going to be equal to root over x square plus y square plus z plus d whole square, right? Z plus d whole square. This will be the distance between minus negative q negative q charge and the point P. So hope you have understood this. Now let me clean this part. So here you can see, so distance between minus q charge and point P is given by is root over x square plus y square plus z plus d whole square. This is the distance between the negative charge and the point P. So now, as we have got the distance between positive charge and P and negative charge Q and P, so we can find the potential due to positive Q charge at P, and we can find the potential at P due to the negative Q charge, and those are here you can see. So potential due to Q positive charge is given by this expression, and due to negative charge is this, right? And net electric potential at the point is given by this expression here you can see. So what we have done, we have taken this Q 4 pi epsilon naught common from these two, right? So here is the expression. Now we need to find the potential on the surface. Here you can see, this is the question: potential, electric field, induced EMF, charge density on an earthed conductor plane, on an earthed conductor plane. So this conductor is being earthed, right, so that its potential is 0. So here you can see, so this is the expression. But when you say on the surface, then in case of on the surface, if P is at this point, suppose this is the point P, this is on the surface, so then z coordinate will be equal to 0. This coordinate will be x comma y comma 0. Z coordinate will be 0, right? So for z is equal to 0, if you put 0 here and here also, then you will get this expression, right? And you can see clearly these two terms are cancelled, and that's why it's become 0, right? 0 into anything is 0, so potential on the surface is 0, right? So now let's move on to next part, electrical field, right? So if you calculate the electrical field at point P, then here we need to we know that electric field at a point P, that gonna be equal to negative gradient of potential. And here you can see that this is infinite surface, this conducting surface is infinite conducting surface. And also you see, let me explain here. If this is the surface and this is the Q, and the electric field due to Q that are normal to this surface, right? Something like this in this direction, okay, normal to this direction. And so we have to take you see, the direction of electric field will be perpendicular to this surface only, that means along z direction. That's why I have written here z cap, so I have taken del z here, okay. We don't need to take this del x of v, del y of v, okay. So hope you have understood this. Now, so if you differentiate v, so what we have got v, right? This expression, if you differentiate this, then what you will get with respect to z, this expression. So here, if you assume this whole thing as root x, and ddx of root x is what? Minus half 1 by root x. Now this is not actually x, so it is x square plus y square plus z minus d whole square. So actually we are differentiating with respect to z, so you can assume this is root z. So now this is function of function. You have to differentiate the terms under the root again. Okay, if you differentiate z square, so here you can see instead of z we have this whole expression. So if you assume this whole thing as z, right, then its derivative will be given by minus half 1 by z. Then again here z is x square plus y square plus z minus d whole square, right? So let me explain it properly. Wait, how to differentiate this? Let me copy this expression. Let me go to a new slide so that I can explain it. So if you differentiate this part, then with respect to z, then what you will get? 1 by root over x square plus y square plus z minus d whole square. So then here you see derivative of this 1 by root z with respect to z. So you can consider that 1 by root z as z to the power minus half, right? If you differentiate it, you will get minus half, then z to the power minus 3 by 2, which can be written as half 1 by z to the power 3 by 2, right? So according to that, then you can write this one as minus 1 by 2 here x square plus y square plus z minus d whole square whole to the power 3 by 2. Now you can see this is not only z, though we are differentiating with respect to z, but here you see derivative of x square with respect to z, that's going to be 0. With respect to z, derivative of y square, that's going to be also 0. Again, if you differentiate this z minus d whole square, then you should get 2z minus d, and again if you differentiate z minus d, then you should get 1 only. So that's why this is the derivative of this, right? So similarly, if you differentiate this part, then you should get minus half 2. Here we have z plus d, so z plus d x square plus y square plus z plus d whole square, that's what you will get, whole square, then whole to the power 3 by 2. And if you put these results here, you can see if you put this to derivative here, then here you can see the above step. So I have put the results here, okay, and as you can see here we have minus sign, and there is also minus, so this two minus will be, if you, when you will put this here, then this minus, if you differentiate this with respect to z, then this minus and this minus will become plus, right? So now let's go back to this. Okay, so now substituting this result here, what we have got, this here 2 cancel, 2 gone, and then this minus sign is being multiplied to these two terms, okay, then we have got this result. So we need electric field on the plane, so at z is equal to 0. Now put z equal to 0, here also z equal to 0, here also 0, z equal to 0, z equal to 0, and doing so we have got this is the electric field on the surface, right, on the conducting plane. And let us find the charge density. So here you see charge density, that's going to be epsilon naught into E, because E is equal to epsilon naught times of charge density, we know that. So here now let's put the result that we have got here, that is E is equal to this one, right? So we have used that result here, and I'm not giving here the z cap because it is a scalar quantity, right? So this is the result, this is the charge density on the surface, right? So hope you have understood this, and if you think this video is helpful, please share with your friends and subscribe the channel if you're new to my channel. Hit the thumbs up button, and also hit the bell icon so that you get notified when new video will be uploaded. Okay, thank you for watching. See you in the next video. Remaining questions will be solved in the next part. Okay, next part will be appear at the end when it will be uploaded, right?